Hello everyone, my name is Jenny Calahan. I am a student at the University of Michigan. I am working on my PhD in astronomy and astrophysics, and I'm excited to tell you a little bit about my research today. I am very interested in the earliest stages of planet formation. So basically, I'm really interested in how our Earth formed and how our entire solar system formed. Our solar system is made of our sun, which is really important. It provides light to us on the earth, which is really essential for life and plants and animals and keeping our water liquid. And we also have a lot of planets in our solar system, of course, including our own Earth. That's us. And I'm just interested in how the entire solar system came to be. And in order to understand that, we actually have to look at some of the prettiest things in the universe. So this is an example of a star-forming region. This is where stars and planets will eventually form. And this is called the Pillars of Creation. It was actually taken by a space telescope called Hubble. So it's a real-life image. It's not an artistic rendering. It's a real-life picture. This is another example of a star-forming region. You can now see more stars, which are really big and bright. Those are baby stars. But the actual birthplace of stars and planets is right here. And that is what I want to start to focus on. This is a clump of dust and gas. And when I say dust, that's kind of similar to the dust in your house. However, this dust is much smaller and made of different material. So this here is our cloud of dust and gas. Due to the force of gravity, so the same force that causes apples to drop from trees, the edges of the cloud will fall inward and more stuff will form in the center. Now, because space isn't perfect, there's also going to be some sort of sideways or spinny motion associated with that downward push of gravity. And that creates a disk-like object to form in the center around the newly formed star. Now, eventually, that cloud of dust and gas either falls onto that disk or goes away, and we're just left with the disk itself surrounding the star. And this disk is called a protoplanetary disk. And it's what I study. Disks are really important to study and understand because eventually this disk will form planets and can form a planetary system like our own solar system. Now, when I focus on protoplanetary disks, there are two properties of the disk that I'd like to know about. One is mass. So we're familiar with mass on Earth because when we say something is massive, we mean something is really heavy or there's a lot of it. So mass is basically how much of something that you have. The other property I'm interested in is temperature. Again, we're familiar with temperature here on the Earth because if we go outside in the summer, it's really hot, so the temperature is really high, or if we go out in the winter, it's really cold, or in our freezer, and that means that the temperature is very low. I can also relate these properties to possible planets that will form within the disk. So if I can know the mass of the disk, I will then know how many possible planets can form and where they can possibly form. And with temperature, that will tell me more about the chemistry inside of the disk. So a disk has a lot of gas in it. So it's made of individual gas particles or molecules. So the little green guys right here. And when they are hot, these gas particles will move around quite a bit. They can hit each other and form different molecules. As opposed to when they are cold, they may actually freeze onto the grains and be too cold to make anything, or they can interact with other molecules also frozen onto those grains. So let's say I wanted to take the temperature inside of a protoplanetary disk. How might I go about doing that? Well, what if we send an astronaut to the nearest protoplanetary disk and give them a thermometer? They can go around in the disk and tell us what the temperature is in different places. Well, there is an issue with that. The nearest protoplanetary disk to us is this many miles away, which is such a big number that I don't even know how to pronounce it. It's just so far away, we'd never be able to get there. Another way to think of that number is that if we traveled at the fastest speed possible in the universe, it would still take us 200 years to get there. So there's no way to directly measure the temperature within a protoplanetary disk. And this is true for most of astronomy. Astronomers need to be very creative in the way that they take their measurements. To understand how exactly I'm able to measure the temperature of a protoplanetary disk, we first need to understand what makes up a disk itself. So if I take a slice of the disk, we can see two main components. The first part is the center of the disk. That's called the disk midplane, and that's where all the big chunks of dust are, and it's where planets will form. The second part of the disk is the atmosphere. And so this is mostly comprised of gas, and it has those individual gas particles or molecules that live way above and beyond the dusty midplane. I get to observe protoplanetary disks with a telescope. And this here may not be what you actually imagine when you think of a telescope. It's actually a special kind of telescope called a radio telescope, and it can detect really low energy light, which is what protoplanetary disks often emit in. I, in particular, observe a certain part of the gas called carbon monoxide. You may have heard of carbon monoxide because you might have a carbon monoxide detector at your home. We as humans can't actually smell carbon monoxide, but it can be very dangerous if we breathe in too much, so that's why we have detectors at home. And it turns out that there's actually a lot of carbon monoxide in space, and it's really great for measuring temperature. And these are actually real observations that I use in my research, taken with a radio telescope, and it shows us where carbon monoxide lives within a disk. My job is to recreate these observations using a computer. I want to recreate these observations using everything I know about disks, physics, chemistry, and how radio observations work. And this is actually what I do every day. And so that means I'm on my laptop a lot. I do a lot of coding. I speak the language of the computer to tell it what to do. I do a lot of reading and learning because I need to learn about protoplanetary disks and chemistry and physics. And of course, I do a lot of problem solving. I encounter a lot of problems that I need to come up with creative solutions for. And so this is really what an astronomer does every day. Eventually, I'm able to recreate these observations to the best of my ability, and they look like this. And so that means that I now have a protoplanetary disk living inside of my computer that represents the protoplanetary disk that I'm observing out in space. And so I can make my own astronaut and have them take their own temperatures, so I can find out where it's really, really hot in the disk and where it's going to be very cold and where it's going to be super cold, which will tell me more about the chemistry and where planets can form. So all in all, I use both observations and computer simulations in order to take the temperature of protoplanetary disks. This is really important because protoplanetary disks eventually form solar systems just like our own. So if we want to understand how plants and our Earth forms and humans and all that important stuff, we first need to understand protoplanetary disks. Thank you so much for listening. I really hope you enjoyed it. If you do have any questions, you can feel free to reach out to me. And yeah, I hope you liked it.